In this video, we'll be discussing question paper 4.1 and 4.3 of 9701 Chemistry Examination Series May-June 2024. In our earlier two videos, we have already discussed question 1 to 3 in the first video and question 4, 5, 6 in the second video. In this video, we'll be discussing the remaining 3 questions. So let's start with question 7 directly. So here is question 7 where it says there are 4 esters A, B, C, D with the molecular formula C6H12O2 and they are shown here. A, B, C, D ester structure are given here. Give the systematic name of the ester A. Now what is ester A? We can see that the alcohol part is here with only 1 carbon and the carboxylic part is having 1, 2, 3, 4 and 5 carbon, that is pent. So our ester is methyl, that is the alcohol part first with the 1 carbon and the carboxylic part next with the 5 carbon, so that is pentanovate. So methyl pentanovate is the systematic name of the ester A. Fine. A mixture of these esters A, B, C and D is analyzed by gas liquid chromatography. The chromatography produced is shown in figure 7.2 and the number of above each peak represents area under the peak. Okay, here it's given the area under each peak is proportional to the mass of the respective ester in the mixture. State what is meant by the retention time. Now what is retention time? It's the time taken by a solute or a substance. You can say by a, I'm writing a substance here, I'm not writing a solute, substance to travel through the column, in a chromatography before it gets detected. So you can say it's the time between the starting time and the time it gets detected. Fine. The next part says calculate the percentage by mass of ester D in the original mixture. Now it says that area under the peak is proportional to its mass. So here it's written what was the ester? Okay, D is having the mass of 38 and the remaining are all this given here. So what's the method we'll be using is 38 divide by the total, that is 14 plus 25 plus 52 plus 38 into 100. That's the percentage by mass of ester D in the original mixture. And if we write the answer in 1 decimal place, it is 29.5%, or you can write it as 29.45%. That was the answer, original answer. Okay, let us go with the C part where it says separate samples of the esters A, B, C, D are analyzed using proton NMR and carbon-13 NMR spectroscopy. Complete the table 7.1 to show the number of peaks in each NMR for the esters B and C. So if we start with the proton NMR of B and C, let's understand how many peaks we'll get for B. So first let's see how many types of proton are there in B. Here we can say here it's CH3, here it is CH2, again CH3 here is CH and the last one is CH3, and you can see that all the protons are of different types. So how many protons we have? 1, 2, 3, 4 and 5. So B have 5 peaks for the proton NMR. Okay, if you look at the structure of C, we can see that here there is CH, it's CH3 and CH3. Now we can see that both these proton are of same type because both of them are bonded to CH. Here it is CH2, here it's here is CH3. So how many types of proton present in C? It's 1 here, 1, 2, 3 and 4. So we can say that B will be having 5 peaks of proton NMR, and in C there will be 4. So let's write that first before we go ahead with the C13 NMR. It's 5 and 4. Now let's check for the carbon 13 NMR, that is how many types of carbon are present in B and C. Now we've already detected about the structure of carbon here. Now if we see here about carbon, there is one more carbon here, and again we can make out that all the carbon are of different types because they are bonded to different groups. So you can say that there are 6 types of carbon present here in B. And in C again there is one more carbon present here, all of different types, but only this 2 carbon are of same. So we can say here are 5 types of carbon in the same way. So let's go ahead and write that in our column 6 and 5. Fine. The next is identify all the esters from A, B, C and D that have at least one triplet peak in their proton NMR spectrum. Now when do we get a triplet peak? Triplet peak is possible only when the adjoining carbon have CH2, that is 2 protons present on the adjoining carbon, adjacent carbon, then only the peak for a particular proton will be triplet. So triplet for these proton will be if the adjoining carbon is CH2, that is carrying 2 protons. So let's go ahead and check that how many of these esters have at least one triplet. So if we have a look at the structure, how many groups have CH2? Yes, we can have CH2 here. So the proton here is bonded to CH2. So 2 plus 1, that is triplet for this proton. So A is definitely having one triplet. Similarly goes for B, because here one of the CH3 is bonded to CH2. Now there are 2 protons on the adjoining carbon, so here B also will get one triplet. Now if we check with the C, now this CH3 is bonded to CH. So the proton here will be having a doublet, not the triplet. This proton is bonded to total 6 proton on one side and 2 more proton on the other side here. So this proton also cannot have a triplet, and this proton is the last proton is bonded to no other carbon, so not possible in C. So C doesn't have any triplet, and same goes for D also, because these are all CH3 bonded to only one carbon. So all these H3 will be having a singlet only because there is no proton on the adjacent. And here is NCH3, one more CH3 which is not bonded to any carbon directly. So no triplet possible here. So the triplet possible are in the esters A and B. So let's write here A and B esters have at least one triplet. Yes. Next part D says compound F is C6H8O3, shows stereoisomerism and effervescence with sodium carbonate. Now stereoisomerism is maybe geometric or optical, so maybe a double bond or a chiral center should be present. Fine. And if it's showing an effervescence with sodium carbonate, then definitely it is having an acid part, that is carboxylic acid is present in the compound F as one of the functional group. If we read the next part, its compound F reacts with alkaline iodine to form yellow precipitate G and compound H. Now if it's reacting with alkaline iodine to form the yellow precipitate G, then G is definitely CHI3, because that's the triiodomethane which shows yellow precipitate. So I'm writing directly CHI3 here. But if iodine is reacting with F, then the F should definitely have one methyl ketone group, or it should have a secondary alcohol. Now let's see what are the possibilities out of these two. What is possible? Compound F reacts with LiAlH4, that's a reducing agent, to form the compound J with C6H12O2. Means one of the oxygen is being reduced to to form O2. One oxygen is removed. Next is compound F reacts with SOCl2 to form compound K, which is C6H7O2Cl. So thionyl chloride is reacting with the carboxylic part to form the acyl chloride. So carboxylic acid is reacting to form K. Compound K then reacts with propane 2-ol to form the compound L. Obviously, if carboxyl acid, acyl chloride is formed, it reacts with propane 2-ol, it's going to form an ester. Ester is going to be compound L. So that was the information we have collected. Now let's understand that how is that possible. So now let's work out for the structure of F. Now, as we have already known that there are 6 carbons. Out of 6 carbon, there is 1 carboxylic acid. So if there is, and also it's undergoing in stereoisomerism, then there should be 1 branch of a methyl group. So let's add that 1 branch of methyl group somewhere, either here or here. We can add anywhere. So 1, 2, 3, 4, 5 and 6 carbon we have already added, and now I'm adding a carboxylic group on the one side. Now here either it should be a ketone or it should be a carboxyl group. Now if we read the third part, it says when it is reduced, you can see that out of 8 hydrogen there are now 12 hydrogen, that is 4 hydrogen added here. Now if it's already a carboxyl group, that is alcohol part, it cannot be further reduced and we cannot add hydrogen. Only the carboxylic group will get reduced to alcohol. So in that case we cannot add 4 hydrogen. So that shows that there should be a ketone which further gets reduced to alcohol, that is carboxyl part, and we can add 1 more hydrogen. So because of that we can make out there is a methyl ketone here. I've added a branch here, but I think you can add a branch on the next carbon also. So that should be the structure of F. Now if we have already drawn CHI3 as in yellow precipitate, then compound H. Now CHI3 is this carbon which is undergoing to form the yellow precipitate. So remaining 5 carbons should be drawn with the carboxylic acid added. Carboxylic acid added to the last carbon. So if we go ahead, out of 6, now I'm drawing 5 carbon, 1, 2, 3, 4 and 5. Okay. Oh sorry, here we have to add a branch here. So here is OH and a double bond here, carboxylic group here. The last ketone group that will also undergo oxidation to form the carboxylic acid. So I'm drawing again a carboxylic acid on the last carbon which has got fragmented, or you can say broken down to form the carboxylic acid. So H is given the structure here. Now LiAlH4, that is a reducing agent. Now as we have already discussed that the carboxylic part and the ketone part will get reduced with the lithium aluminium hydrate. So we'll draw the same structure, but in place of carboxylic acid we'll be drawing only the alcohol here and an alcohol here. The remaining carbon remains as such. The carboxylic and the ketone part gets reduced. Okay. Thionyl chloride is added, that is going to react with the carboxylic part to form the acyl chloride. Remaining remains as such. So let me draw the structure here, and the ketone part remains, the branch part remains same, and the acyl chloride is formed here. Yes, this is acyl chloride, fine, written here. Now that is going to react with the propane 2-ol, that is the carboxylic part, that is acyl chloride, is going to react with the propane 2-ol to form the ester. Now what is propane 2-ol? We have propane 2-ol with the alcohol on the second carbon. Now that is going to react here. So understand how are we going to add and draw the structure of an ester. The remaining part remains the same. the double bond O remains also same, but here the O of these propane 2-ol will be added. Now that is bonded to a carbon with 2 branch, right? So this is how we are going to draw the structure. Okay, one more part I forgot to tell you is that if we count the hydrogen, here, there are 8 hydrogens, so there should be one double bond somewhere here. So if I add a double bond here, everywhere we'll be adding a double bond, because if you count the hydrogen, there is hydrogen number less, so I have to add a double bond everywhere here, because the double bond will not get changed. The double bond is not undergoing any reaction, so here also I'm drawing a double bond. The ketone part here again remains the same, and this is how I've drawn the ester. I've added 3 carbon, 1, 2 and 3, and the alcohol part is added to the carboxylic acid, that is acyl chloride part, forming the ester. So this is how you make the structure from the given information. Count the hydrogen, because the last when I counted hydrogen, I realized that there are less number of hydrogen mentioned in the molecular formula compared to my structure. So I need to add a double bond to mention about the less number of hydrogen. Okay, let's start with the question 8, 9. 8 is Neotame is an artificial sweetener added to some foods. So here is the structure of Neotame given. State the number of chiral carbon atoms in a molecule of Neotame. Now if here the structure is given, we need to count the number of chiral carbon present. Now chiral carbon is present only when there is a branch. Okay, so if here is a branch, but this carbon cannot be a chiral carbon, because there are same types of 3 groups present, that is CH3. All the 3 groups present to the carbon are same, only the remaining one is different. Here are CH2, so not possible. Here also not possible the chiral carbon. Here is one carbon which is possibly a chiral center, because that's bonded to 4 different groups with 4th group as hydrogen. So this is definitely a chiral carbon. So this is the first carbon I'm mentioning with an asterisk sign. There is one more carbon here, again I'll mention it as an asterisk. Why? Because there is 3 different groups, the 4th group being the hydrogen. So there are 2 total carbon present here, which is chiral center. Again, next carbon here is also not a chiral carbon, because there are 2 hydrogen present here. So 2 chiral carbon present in the molecule of Neotame. Fine. Neotame contains the arene functional group. Identify all other functional groups present in Neotame. Yes, arene group, that is benzene group, is present here. Other than that, we have COO, so ester group. We have CONH group, so that's an amide group. We have NH group here, which is a amine group. We have carboxylic acid. Okay, so these are the 4 groups present here. So ester, amide, amine and carboxylic group. So ester, amide, amine and carboxylic acid. Carboxylic acids are the 4 functional groups present in Neotame other than arene. The next B part says Neotame reacts with excess of hot NaOH aqueous to form 3 organic products. Now state the 2 types of reaction that occurs when the Neotame reacts with hot NaOH. Now if it's hot NaOH reacting here, let me rub out everything, the circles I've made. Okay, here are all the extra circles and the notice labels gone. Let's see now where are the parts where hot NaOH is going to react. Now hot NaOH is an alkali, strong alkali, so it's definitely going to react with the acid part to form a salt, so that's an acid base reaction. And other than that, hot NaOH is also an hydrolyzing agent where the ester or the amide group will be hydrolyzed to break down into 3 different groups, right? So then here we can say that the 2 reactions occurring will be, one will be hydrolysis. hydrolysis of the ester and the amide group, and an acid-base reaction where it's going to react with the carboxylic acid to form the sodium salt. Okay, here is the structure of Neotame given again, and draw the structure of the three organic products formed from the reaction of Neotame with an excess of hot NaOH. Now, as I said, hot NaOH is going to break down the ester group into alcohol and carboxylic group. So, the alcohol group which is going to form is the methanol. So, directly if we draw the structure, it's going to be CH3OH, methanol group. Now, if we have a look here, it's going to break from here and here. So second part will be somewhere here with the benzene ring. So let me draw the benzene ring given here, similar benzene ring. Okay, my benzene is little distorted, but you can definitely make it up better than me. Let me draw this part. Now this is going to form a carboxylic acid. So I've drawn a carboxylic acid, and the remaining part is going to form the amine group getting hydrolyzed. So I'm drawing the amine group, which is hydrogen being added here and OH getting added on the carboxylic group. So I've drawn the center circle here where I've added hydrogen here and I've added the OH part here to form the carboxylic group. Yes, I think it's very clear. OH group added to the carboxylic part and H hydrogen added to the amine part to form NH2, and this is how I drawn the middle structure, and the remaining third structure will be somewhere here from this part to the last part. Now let's draw that structure. We can see that there is one carbon with the 3 branch and then 2 more carbon added with the NH group here. So let me draw that first. Here 1, 2, 3 added, then the 2 carbon more added, and then the NH group added here, right? That's how I'm going to draw NH group added here. Then the remaining part NH, we have 1 more carbon, then the carboxylic part, and then the branch with 1 more carboxylic part. So let's see. Yes, 1 more carbon with the carboxylic part, and then the branch here again with the carboxylic part. Yes, so this is how the third group will be there, where we can see that here we have added the carboxylic OH group here to form the third fragment after hydrolysis. So here the question 8 also ends. Let's start with question 9. Starting with question 9, it says samples of phenol are reacted separately with sodium and dilute nitric acid. Here is phenol given. Write the equation for the reaction of C6H5OH, that is phenol with sodium. Now a phenol is little acidic, so it reacts with a sodium to form an sodium salt. So we can write it C6H5ONa, and hydrogen is removed out here as an hydrogen gas. Now we can balance it by adding 2 and 2 here, or we can keep all that as 1 and add in half here in front of hydrogen. So that's totally our choice. How do we balance it? So let's read the next part, where draw the structures of the 2 major isomeric organic products formed in the reaction of phenol with dilute nitric acid. So when dilute nitric acid is added to phenol, the nitro group will be added to the benzene ring, but with 2 different possibilities, that is on the 2nd position or the 4th position, because phenol, that is OH, is an electron donating group. So nitro group can be added to the 2nd group or 2nd carbon, or nitro group can be added to the 4th carbon, that is 4th position. So here I can add the nitro group. It's dilute nitric acid, so only one of the nitro group will be added to phenol. But if we use concentrated nitric acid, all the 3 positions, that is 2, 4 and 6 position of the phenol will be occupied by the nitro group. But here it's nitro dilute, so only 2 nitro group will be added separately to the 2 different positions. The B part, here salicylic acid can be synthesized from phenol, and the structure of salicylic acid is given here. One of the steps in this synthesis is the electrophilic substitution reaction of the carbon dioxide with the phenoxide ion, that is C6H5O-, that is electrophilic substitution reaction of carbon dioxide with phenoxide, and understand this is electrophilic substitution reaction. Complete the mechanism in figure 9.3 for the reaction of the phenoxide ion with the CO2 group. Okay, here are the phenoxide ion given and CO2 group given here. Include all the relevant curly arrows, dipoles, charges. Draw the structure of the organic intermediate. So if we draw the partial charges, here will be partial negative, partial positive and partial negative on this position. So because of that, we'll draw an arrow from the double bond, that is pi bonding system, which is having an high electron cloud density towards the carbon positive. And this is how it's going to form an intermediate. So let's draw the benzene ring, which is drawn and shown here to us with the phenoxide ion. So O- is drawn. Now the carbon dioxide will be added here, but carbon dioxide as such cannot be added because that's further going to form the carboxylic acid group, that is COO- or COOH. So obviously it's going to form in COO- being added here. So in that case we need to draw an curly arrow on the carbon dioxide showing as one of the double bond being passed on to one of the O group forming O-. So obviously we need to draw O- and double bond O here, or you can directly write it as COO- group also. And we need to remember that the carbon on which the carboxyl group is added should not have the pi bonding system. So the remaining carbon I am drawing in partial pi bonding system with a positive charge being shown in the middle, and this is the organic intermediate with the positive arene group with O- and CO- being shown here, intermediate fully drawn. Now so if this is the COO- and how, okay, so one more thing is forgotten here, that is H being as an intermediate still present, and then we show an curly arrow from the bond of H to this positive benzene to form the complete pi bonding system here. So yes, don't forget that. And so the byproduct form will be H plus, which is being removed here from this benzene where the bond of hydrogen will be broken down. Okay, if we read the next part, some synthesis use a Diels-Alder reaction, which normally involves a diene and an alkene reacting together to form a cyclohexene. The first part of the question says draw 3 curly arrows in the figure 9.4 to complete the mechanism of the Diels-Alder reaction between buta-1,3-diene and ethene. So here is ethene here, buta-1,3-diene is shown here, and we can see the structure of the cyclohexene where the double bond alkene, that is ethene being added here, the double bond here is broken, and the 2 double bond which were present in the buta-1,3-diene is changed to the single double bond here. That shows that the shifting of the double bond or the pi bonding is being done here. So in that case, if we draw the 3 curly arrows, it's clearly mentioned draw 3 curly arrows. So I should draw one of the curly arrow here, this bond being shifting here to form a complete bond here, this bond is completed here, and this bond being again shifting to form one of the bond here. So these are the 3 curly arrows I'll draw, or you can draw in the reverse direction also, doesn't make any difference. So curly arrows are drawn here, 3 curly arrows shown here. The next part, another Diels-Alder reaction of buta-1,3-diene is shown in the figure 9.5. okay, here again buta-1,3-diene is shown here. There is one more cyclo structure present with the 6 carbon, but the ring is a penta, that is a 5-sided carbon ring. with one double bond. Now predict the product formed in this reaction. The similar reaction will occur where the bonds will be shifting here, and the bond will be shifting here. So in short, you can say that this 2 carbon will bond with this buta-1,3-diene to form a complete ring with the single double bond. So that's what had happened in the earlier reaction shown, and this is how the reaction had occurred with the 6 carbon chain. We can see here the 6 carbon chain with cyclohexene with one double bond shown here. But then these are the only 2 carbon taking part in forming this cyclohexene. So the remaining carbon 1, 2, 3 and the 4th carbon remains the same with no change. So I should draw the remaining carbon as such without any change and a branch here. Again, my ring is little distorted here. You can draw a better one, but I hope you understood what am I doing it. Only the 2 carbon circled here is taking part to form the cyclohexene. The remaining carbon chain will remain unchanged and can be drawn same as such shown in the question. Yes, so here I think all the questions are very clear, and I think I have completed with the paper all the question 9 questions are completed, solved in 3 different videos with 3 questions in each video. You can refer the other videos also for the remaining questions.